Right. Okay, good. So welcome back to on the One World seminar on optimization. So today is my great pleasure to introduce Uday Shanbhag from Pennsylvania State University. Uday is a well-known expert on stochastic optimization, stochastic variational inequalities, stochastic Nash games, and in general, he brought, I think, a big contribution to the mathematical programming community, making game theory also a bit more popular in that field and showing the interesting optimization aspects in that area. Uday is a well-known scientist in our community. He's, among other things, editor of the Science Journal of Optimization, or one of the editorial editors of the Science Journal of Optimization. He's also serving on the editorial board of the IEEE TAC journal. He's been in the prize committee of many important student awards, like the Nicholson Prize or the Tucker Prize. And yeah, I think we're all very happy to have you, Uday, here on board in our seminar series. So the floor is now yours. And I guess we will continue the typical tradition that you are willing to receive questions during your talk as well, right?
Yeah,
So
absolutely.
great.
And I don't know whether the chat thing is working, Matthias, but I'll
Yeah,
assume people will just
usually
talk.
so it depends a lot on the participants. Many people write questions in the chat and the moderator is then picking up the question, but sometimes also people just ask questions directly. It's quite
Okay.
variable. We are a bit liberal here. I hope you don't mind with that
Oh, no, no, not
policy.
at all. In fact, if I miss a chat question, because sometimes I'm trying to
No,
look for the
we will
bot.
monitor it for you. We will
Okay, okay.
monitor it for you, sure. Yes.
Okay. So
Okay.
just feel free to
So
talk.
Uday, floor is yours. It's a great pleasure to have you.
Okay. Well, thank you so much, Matthias, for the very warm introduction. It's an honor to be here. It's a remarkable set of speakers, and I want to commend you and Raju and the rest of the organizers for doing the community such a service by organizing this in this what is one of the most difficult periods that this world has faced. So this is a nice bit of escape for a lot of us to actually do some technical work and talk about it. So I'm very grateful to have this opportunity. So this work is joined with my so this is I'm going to be going through a collection of results, and this is joint work with my postdoctoral scholar Jin Long, who's now a faculty member in Tongji, and of course Zhongxi Pang and Subhrajit Sen, both of whom do not need an introduction. So I'm going to oh, okay, so this class of problems that we are looking at are essentially variants of the n-player Nash equilibrium problem, and the focus of this work is to really look at the role of uncertainty and the need to develop distributed algorithms. But to ensure that everyone's on the same page, I'm going to spend some time introducing the problem. Okay, so we're looking at an n-player problem where n script denotes the set of players. Um, the strategy is going to be denoted by x sub I, and the strategy set for player I is going to be denoted by capital Xi, where x is a vector with x1 to xn, and it lies in the Cartesian product of x sub I, where x sub I, the Cartesian product is going to be denoted by x. Okay. We're going to assume that. Oh well, I'll make a note of the assumptions shortly. So in an n-player Nash equilibrium problem, which owes its formulation to the seminal work by John Nash in the 50s, each player minimizes its objective given rival actions. Given x minus I, the ith player tries to minimize or minimizes fi in xi. And x star is denoted as a Nash equilibrium if for any I in n script, fi of xi star x minus I star is less than fi of xi x minus I star for all xi. Okay, so the Nash criterion holds. Okay. And so in words, what that means is no player can improve a payoff by unilaterally deviating from strategy xi star. So most of you who are familiar with this class of problems will see this as as something that you're quite familiar with. The assumptions that we are going to be employing to a large extent in this work are that X sub I is a closed convex set, and Fi is convex and Xi on an open set containing capital Xi. Okay, and so this class of non-cooperative games is a class of static convex games in effect. Time permitting, at the end, I'll talk a bit about some of the work we've done on the non-convex side, but I'm not certain if I'll get time. But if there is interest, and if if a question is raised, I'll talk a bit more about the work we've done on the non-convex side as well. So let's start by just introducing one of the most popular techniques for computing a Nash equilibrium in this context. And this is the synchronous gradient response scheme. And the term synchronous, the qualifier is particularly relevant because I'm going to be looking at weakenings of this, looking at asynchronous regimes as well. Okay. So loosely speaking, in gradient response schemes, player I employs the gradient response given current rival strategies. And what exactly does that mean? It means that every player simultaneously computes her gradient response by essentially looking at this projected gradient step. Essentially takes, given strategies, given the current strategy value of X sub ik, it moves along the negative gradient direction using step length gamma ik and projects back to the set X sub. Okay, so the standard projected gradient update, and each player simultaneously computes this. And essentially computing such a gradient response requires players to have access to essentially some oracle that produces a gradient and X minus ik. Essentially, it needs to have access to all current rival information. Okay, and so this lends itself to partially distributed implementations. And under some conditions, and I'll provide some literature here subsequently, synchronous gradient response schemes produce sequences that converge to a Nash equilibrium. Just notational issues. This pi of xi, of course, is the projection of the argument onto X sub I. Okay, so this is the canonical gradient response scheme, and essentially, and of course this talk doesn't pertain directly to gradient response, but essentially, if F is the concatenated gradient map, okay, if F is the concatenated gradient map where essentially each element represents the gradient map associated with the ith player, then what is well known is that if F is L-Lipschitz and eta strongly monotone, and if the step lengths are suitably small, then this gradient scheme converges to a unique Nash equilibrium. And there's tons of work to kind of look at questions where if each player chooses her own step length sequence and there's some coordination across these step length sequences, does convergence ensue? And it turns out it does. Okay, and of course, but using that as a basis, I want to kind of go from there and talk about variants of these schemes, because this is something that assumes relevance later in the talk. One of the challenges with this previous scheme is the requirement that essentially F be strongly monotone. Now there are avenues to get around that using regularization, and that's one of the points I make next. But this is not the only resolution when you have to deal with mere monotonicity. This is one resolution. Okay, so essentially, remember we had a projected gradient step. Now we have a projected gradient step, but instead of using the gradient, we use the gradient along with a regularization. Okay, so this is, for those of you familiar with this looks very close to the Tikhonov regularization, but with one key difference. At every step, you update not just the strategy, but also the value of the Tikhonov sequence, and you do it at every step. So if F is monotone, then under suitable conditions on the step length sequence and the regularization sequence, this synchronous regularized gradient scheme also converges, and it converges to the least norm Nash equilibrium. Okay, but this is by no means the only way to employ single projection schemes. There are other ways to do it. So for instance, if when you have strongly monotone maps, I want to just kind of point out some of the early work came from the work by Tamer Bashar with his doctoral student Tanshu Alpakan. Lakra Pavel and her co-authors have also done some crucial work in building up to this. When we started looking at this question, we looked at iterative regularization, and this was essentially a single projection scheme. In this work, we also looked at iterative proc schemes, but I won't go into that here. But that's not the only way to deal with single projections, right? So there's some wonderful work that was done by Yura Malitsky in 2015, where they have the projected reflected gradient methods. So so this is not meant to be an exhaustive summary of research. And why do we make a big deal of single projections? Because if you're dealing with merely monotone problems, then the traditional approach has been to use an extra gradient framework where essentially at every step you have two projections rather than one. So the per iteration complexity, of course, gets doubled. And the work by Mlitsky and the regularization work obviates that. Okay. Now, of course, one of the key shortcomings in this, particularly from folks who are, from economics or game theory, they would see this as not being fully rational, right? And so the question is, how do you kind of obviate that? So the standard approach, of course, is to use best response schemes rather than gradient response schemes. Okay, and so I want to give a quick summary of synchronous best response schemes. So in a best response scheme, rather than taking a projected gradient step, here every player actually computes his or her best response. So what is the best response? So given rival strategies, the ith player minimizes her objective, right? And essentially that's the best response. And essentially computing a best response requires player I to know f sub I in analytical form, and have access to rival strategies x minus ik. Okay, this also lends itself to some distributed implementations, but one challenge is that best response schemes may converge, but they may also cycle. Okay, so there are well-known examples where you can show that best response schemes lead to cycles. Okay, so here's a variant of this best response scheme called a proximal best response scheme, which originates, at least to the best of our knowledge, from the work by Fakine and Bang. Okay, so here instead of computing the best response in the traditional way that I just mentioned, you add this additional term, which is essentially a proximal. Okay, and of course this makes the problem nice. The best response is now unique. And then the problem that you're working with is strongly convex. Okay. Again, there are some conditions under which proximal best response schemes converge to a Nash equilibrium. And as I mentioned, the analysis of this was conducted by Fakine and Pang in 2009, right? And essentially, what they required was that a suitable spectral property held. Now, that suitable spectral property relied on, of course, twice differentiability. Okay, and that's, of course, a strong assumption. And one of the goals of our ongoing work is to try and see whether some of these requirements can be beaten. But this being amongst the first, the first efforts, we maintain this requirement that we have the spectral property holding. And under the spectral property, you can actually show that geometric convergence ensues. Okay. I don't want to get into this property, but it suffices to hold that it's some spectral property. But on that basis, you can actually construct variants of this best response framework. So here's one variant. In this variant, you have what is called a randomized proximal best response scheme. So when I mean randomized here, what I'm alluding to is that with some probability, a particular player or a set of players is allowed to update, and other players do not update their strategy. Okay, and this is particularly relevant when you're working with large networks, and this protocol is being employed for effecting distributed control. Okay, and so this goes back to the work by Jason Marden and Jeff Sharma and so on, where they used games to effect distributed control. Okay. So this was randomized proximal best response. Only difference here, of course, is, as I mentioned, that I want to emphasize, is that some subset of players update while other players do not modify their update. Okay, so there's, again, tons of work on best response schemes. The work that has been particularly relevant and salient in our in developing our work is the early work by Fakine and Pang, and then the subsequent work by Aldo Scutari with Francisco Fakine and others. Okay, and of course Aldo has done a lot of work on the signal processing side in terms of extending some of these and refining these schemes. But in a lot of their work, their focus has been on settings where the best response update can be computed in its closed form. Okay. And that's allowed them to develop very efficient algorithms in some of these settings. Okay, so now what I want to do is look at the stochastic variant of this. Okay, so the stochastic variant, at least in terms of this particular framing, pertains to settings where the objective is actually expectation value. Okay, so it's an expectation value problem, and essentially a direct extension of gradient response or best response schemes is impossible because it requires access to either the gradient of the expectation, which is challenging if you're working with the general probability spaces. Having access to integrals and their expectations is not something you can take for granted, and you should be able to evaluate those in finite time, and that's clearly not possible. So then we appeal to the existence of a stochastic first order oracle, which is very standard in the stochastic optimization community, right? So I'm going to make this assumption that for those of you familiar with stochastic optimization, you'd find quite natural, right? So what I'm going to assume is that essentially I have access to an unbiased oracle, which produces a sampled gradient, and I also have I impose a requirement that the subgradients are bounded, or the gradients in this case are bounded, okay, uniformly so. Okay, so one of the benefits of not benefits, it's actually quite crucial. Given that we have convexity, we know that an equilibrium of this stochastic Nash equilibrium problem satisfies or is a solution to a suitably defined variational inequality problem, right? And in this particular case, this variational inequality problem is characterized by a mapping whose components are indeed expectation value. Okay, and that's not surprising. Okay, and so essentially, algorithms for stochastic variational inequalities, or SVIs, are closely related to schemes for computing Nash equilibria, particularly on the first order side. Okay, particularly on the first order side, but not necessarily on the best response side. There hasn't been as much. Okay. So I'm going to present, just kind of initiate our discussion from the synchronous stochastic gradient response scheme. So in the synchronous stochastic gradient response scheme, instead of using the projected, just moving along the negative gradient direction, you compute or you obtain a sample from that oracle that I mentioned, and essentially this, for those of you familiar with stochastic gradient descent or stochastic approximation, will see this as just being the counterpart in the game theoretic regime, where each player computes a stochastic gradient step. Okay. So now, and of course, in this particular case, there's been a lot of work on stochastic gradient descent, and naturally, I'm not going to be able to review that. But what I want to do is just allude to some of the crucial work that has been particularly relevant in the context of resolving stochastic variational inequality problems, because it's closely tied. So amongst the earliest work that we know, of course, is the work by Haoyang Zhang and Weifu Xu in 2008, where they proved almost sure convergence for strongly monotone and Lipschitz continuous maps. And they also have some results under weaker conditions. There's the seminal paper by Juditsky, Nemirovsky, and Torvald. Subsequently, there's work by George Lan and his student in 2015. We worked on some results for almost sure convergence for both monotone and Lipschitz maps under single projection regularized schemes. This is what I just mentioned. This is work with my friend and co-author Angelia and our doctoral student Jayesh. And then we trying to look at non-Lipschitzian regimes by using random smoothing. But there's ton of work, okay, in this regime, and I don't intend to kind of get into this here because that's not the focus of this talk. But what I want to do here is to motivate our question. So our question here is twofold. So the first is that I don't have access to a closed form expression of the proximal best response line. Since it's unavailable in finite time because the objective is expectation value. And so the question is, can I develop an inexact proximal best response framework where I approximate the best response by using an inner stochastic approximation scheme that runs for a finite but increasing number of steps that I prescribe, right? That the algorithm designer prescribes. And then when can we extend this? So this seems like a fairly simple idea. You've got a nasty stochastic optimization problem as your sub problem, right? And in some sense, you don't want to come up with a framework which is a 2 time scale framework where you say, I'm going to go and solve that exactly. And you can't do that in finite time. So instead, what you do is you come up with an inexact solution of prescribed accuracy, whose accuracy is then driven to 0 as you proceed through the scheme. Okay, and this is a kind of a standard avenue that optimizers have been employing. And then what we do is we add layers to this. We say, okay, you've got a framework that can deal with synchronicity. Can you deal with the asynchronous variant? And can you deal with the randomized regime? And to what extent do these weakenings allow you to still claim convergence? And to what extent are the rate statements affected and the complexity statements affected by this weakening? Okay. The second part of this work actually looks at a very recent class of problems that has assumed relevance, and this is the class of so if you're interested in computing Nash equilibria via distributed framework, where players do not need to know their rival decisions, how would you do it? Can you essentially use communications with your neighbors to construct a framework which in the limit provides you with the Nash equilibrium? Okay, so this requires the addition of a consensus layer. And of course, we restrict our interest to a class of aggregative games in this case. Okay, okay, so let's proceed. So in this particular case, I'm going to be working with closed, compact, and convex sets for this particular part. And I'm going to be working under the regime that Fi is C2 and Xi or an open set containing Xi, capital Xi. And the reason for this is quite obvious. The reason is that we need the spectral property to hold. And that's one of the shortcomings of this best response framework. So it's important for us to know these shortcomings because that provides us with new questions to ask. And this is one such question that I'm currently pondering. Okay. So here's the proximal best response map that I mentioned. Essentially, you're looking at getting an argmin of this, and this decomposes into player-specific problems. And essentially now you can see this is a strongly convex stochastic optimization problem. And this proximal term is crucial in ensuring that. So we have access to the precise convexity parameter of this optimization problem. Okay. So here's the first scheme and formalized. Essentially, we do exactly what we did in the synchronous proximal best response with one key difference. We essentially compute it inexactly with where the inexactness is captured by this epsilon I k plus 1. So this is the inexactness sequence. And essentially, this inexactness sequence is of course going to be driven to 0 at a suitable rate. And I'm just going to say it's bounded. In this particular case, this epsilon k plus 1 is a random variable, of course. And what we're going to assume is that the conditional second moment is bounded by alpha I squared k, almost surely. And I'm going to show you that actually happens. And you can actually construct an inexact solution that allows you to claim this. Okay. So how do you compute this? How do you compute this inexact solution? Well, you just run a set of stochastic approximation steps, standard kind of tool. And in this particular case, we employ a diminishing step length sequence. And given that, so you can just appeal to the error bounds of stochastic approximation. You can find these in most places, but amongst the most well-known results is the work by Nemirovsky and all in 2009. And I don't want to get into this, but it's suffice to say that you have these sublinear rates that emerge in strongly convex regimes, right? So you can essentially say that after k steps, the conditional second moment of this error is bounded by some order of 1 upon t, okay, if you're taking t steps. And once you have that, what this tells you is that this essentially becomes alpha I squared k. It's qi upon ji k, where ji k represents the number of steps that player I takes at the kth step. Now, the one point I want to emphasize here is that how does this impact the time scale of the scheme if you're going to implement it, right? So does this now reduce to a 2-time scale scheme because the inner problem has to be run, for some arbitrary number of iterations? So our contention is no, that essentially what happens is that when you run the scheme, every player knows exactly how many steps he or she needs to go through before she updates, right? So there isn't this arbitrariness in terms of how many steps you need to run and you're waiting. It's not like that. You're essentially going through this number of steps. It's a prescribed number of steps. The steps are cheap enough that you know that they're computable, and then you proceed. Okay. And so under this regime, of course, you can show that almost show convergence ensues. It's not difficult to show this. And you can also show suitable convergence both in mean, and you can actually show the variance of this XK sequence goes to 0. Okay, so that's not difficult to do. What is more interesting is that you can actually show geometric convergence. Again, this is not altogether surprising that you can show geometric convergence because remember, you had the spectral property at the outset. So the deterministic scheme displays a geometric rate of convergence. Now you're working with an inexact proximal best response scheme. And what you're going to have is that error that ensues has to be driven to 0 at a geometric rate to ensure that you recover the geometric rate that the deterministic scheme gives us. Okay, and so that's exactly what we do. And based on the choice of this, the choice of this eta. And what is eta? If you remember, we had this alpha ik, which captures the rate at which you need to, the exactness with which you need to solve the stochastic subproblem. And here what we're saying is that if alpha ik is going to 0 at a geometric rate, then essentially what's going to happen is that you need to get solutions, you need to get accurate solutions where the accuracy is being driven to 0 at that geometric rate, which means that the number of steps that you need to take have to increase quite rapidly. Now, as we proceed, I'll talk about avenues around that. How do you get around this need to kind of solve these to high degrees of exactness? Now, somebody might say, well, this is problematic because you need to take a lot of steps. Remember, we're trying to mimic best response. Our goal was to mimic best response. If you try and take a single step.
Can I ask a question here?
Yeah,
so you need equality of the alpha ik with the eta k, or is it just sufficient to have a majorization here?
It's just a majorization here because this is in our control. Because alpha ik is in our control. We just set it as eta ik.
Okay.
Because remember, this alpha ik is right here. It's just, see this? It's just, so it's something that we choose. So if we can actually prescribe what JIK is based on alpha ik. And alpha ik is just set to some eta raised to k.
Okay. Yeah. Sure.
So then, So if you want to mimic best response, then you have to do this. Now, of course, a question can be raised, do you want to mimic best response? So that's a separate question. There are settings where you're looking to mimic best response, and if you do, then this is what it takes. But as we move through the talk, I'll talk about avenues where this might be quite an imposition in terms of the sampling rate, right? So I've talked to Matthias about this as well. In that, if you try and raise sampling rates at a geometric rate, this tends to be problematic. How do you get around that? So you can actually look at polynomial rates, and you can choose that as a dial, and we'll talk about that downstream. Okay.
So we have a question in the chat. Sorry.
Yeah.
So Konstantin, would you like to ask the question?
So for me, of course, it's maybe a new material for me, but typically in stochastic approximation, you don't have a geometric convergence rate. So it's very surprising that you achieve geometric convergence rate. And I didn't get an intuition. Why did you get this? So if you
that's a very good question, Constant. Yeah, Constant, that's a very good question. So I don't get geometric convergence rate in the stochastic approximation scheme. What I do is, so if you look at this problem, right? So this problem is a stochastic optimization problem. What I do is, I essentially, to get a solution of the stochastic optimization problem, I take a number of steps. If I take enough steps, I get an error. I get some error, right? Now, in consecutive iterations, if I keep increasing the number of
it's like double loops. So in one loop, you hide a lot of auxiliary steps.
Exactly. But
okay,
remember
now it's clear, yeah.
But the second loop, Constantine, is not a loop which is run forever. It's run for a prescribed number of iterations. Okay, so in that sense, you can look at it as basically a single loop where each part, each iterate in the single loop takes longer and longer, but it takes a prescribed amount of time.
Okay, now the intuition is clear. Thanks a lot.
Okay. So then, so going and analyzing the iteration complexity is a little bit of work, but you're able to show that you get an iteration complexity which is of this, and this is the iteration complexity in inner stochastic gradient steps. So this is of the order of square root n over epsilon the whole squared and a log term. Okay. Now, what you'll notice is this matches the canonical sample complexity of stochastic approximation. But what is not clear to us is whether this square root n, right, this relationship is tight. And I don't have an answer for that. So I want to kind of be honest because I'm curious if other people have looked at this question. So clearly, of course, when n is 1, everything is nice. But the question is, as n becomes larger, are there, does this match some sort of well-known lower bound? And I don't have an answer for that. Okay, so this is our first result on iteration complexity. And you can see that if you compare this to stochastic gradient schemes for a particular problem that we looked at, you can see that this is the proposed synchronous algorithm. What you notice is and this is important for you to see, that when you're working with best response schemes, you only communicate once you've computed an inexact best response. You can see there's a vast difference in the communication levels, right? So Matthias, can you see my cursor? I can't tell. Is it?
Yeah, it's visible.
Yeah, okay, cool. So you can see that essentially the empirical communication complexity doesn't grow significantly. But on the other hand, if you're looking at stochastic gradient schemes where you communicate after every gradient step, then this is much worse. On the other hand, of course, the empirical iteration complexity grows faster for our synchronous algorithm in terms of gradient steps. Okay, so I want to kind of draw this distinction. Now, if you look at the asynchronous regime, so I want to kind of talk about the asynchronous regime. So in the asynchronous regime, we're going to assume that players might not be able to make simultaneous updates, nor have access to their rivals' latest information. Okay, so I'm going to denote T sub I as a set of times where player I updates X sub I. Okay, and Y sub IK refers to a vector with delayed information, where D sub I K, I1K to INK represents the communication delay. Okay, so essentially what happens is that when a player makes an update, then it may be that she only has access to delayed information from some other player. Okay, and what we're going to be assuming is, and so if you look at some of the work that's done in the regime of asynchronous algorithms, some of these assumptions you see are inherited from there. So we have what is called an almost cyclic rule, which just says that that each player has to update her decision once during some interval B sub 1. Okay, so this basically says if B1 is large, it means that essentially a player can go a long way before updating. If B1 is 1, you're back to the setting where essentially a player updates every time. B sub 2 represents the bounds on the delay. If B sub 2 is large, it means that I can have access to highly delayed information. If B sub 2 is small, it means that I need extremely fresh information. Okay, so here's the inexact proximal scheme, the asynchronous variant of this. So essentially in the asynchronous variant, what happens is that essentially Y sub IK is a vector with the delayed information, and this D sub IK is essentially associated with these delay vectors. And now what you have is so basically T sub I represents these. So just to remind you, T sub I is a set of times where player I updates X sub I. So if it turns out that at epoch K lies in T sub I, it means that essentially the ith player will update, and if not, then she will not update. Okay, simple idea, but again, the nastiness is hidden in this structure. Okay. And so what you want to see, what you want to observe is that you can again recover linear convergence in the outer best response steps. Okay. And I'm going to tell you where these subtle differences emerge. And you can also show that there is that you can derive iteration complexities. And so I want to just point out this, okay, because with the paucity of time, it's hard to go through everything, but I want to just kind of take your attention to this iteration complexity. So you remember last time it was 1 upon epsilon squared, and there was a square root n term. So the square root n dependence is the same, but what happens is that this exponent changes, okay? So it gets scaled by B1. Remember what B1 is. If B1 is 1, it means you're updating at every point, which means you get something very similar to what you had before. If B1 is large, then this exponent gets affected, okay? Similarly, if B2 is small, it means that you're back in the original world. If B2 becomes larger, then this again gets scaled, okay? So that's the impact. It directly affects the exponent. And you'll see this when I do some, I demonstrate some numerics. So you can see it here. Mm-hmm. So if you look at this, in this case, B1 is 1, and the communication delays are independently generated from a uniform distribution from 1 to B2. So if you have B2 increasing, you get this kind of behavior where essentially, you see these kind of jumps, okay? Now let's just look at the randomized version. So the randomized best response scheme inherits its ideas originally from the work that Yuri Nesterov did in 2012 when they looked at the randomized block coordinate descent. And there's been work done after that in this regime, where there's a fair amount, including by Peter Richterich and Martin Takach. There's work by Convergence and Pesquet in the context of fixed point problems. And the idea here is that essentially at every iteration, essentially with some probability, you have one of the, some subset of players who are selected with some probability and they update, okay? And so this is the structure for the randomized and exact proximal best response scheme. I want to jump through this because this is in some sense similar to the other one because I have, I think, 10 minutes or 12 minutes left. Okay, again, you can get very similar types of results. The key differences, of course, are in terms of the iteration complexity, where you have an impact showing up in the exponent, okay? And what you notice again is that the impact gets mitigated if you ensure that the PIs go to 1. So if you're always kind of being asked to update, then you get very similar behavior. And of course, what you also observe is that the synchronous algorithm will always perform better empirically and of course theoretically than its asynchronous and its randomized counterpart. And so we have some results to kind of reflect that. Okay. And none of this is surprising by any means. But what is useful to know is that some of these statements can be characterized. Now,
I have a question here. So you never parameterized the numerics also with the size of the network. How much is it scaling with the size?
So that's a very good question. So what we found was that we were able to show the scaling in terms of square root n. So I haven't done that here. We do have some results in the paper. So I actually wanted to point out 2 or 3 things that we don't have here. One is, of course, the scaling result. The other is that what happens when the problem that you have becomes more challenging. So for instance, if you had 2-stage stochastic Nash equilibrium problems, then what you have is that the player-specific problems are nastier. What happens if you have risk measures? So a lot of that stuff can be actually managed within this because all of the nastiness goes into the stochastic subproblem. And as long as you can call a solver with a suitable error bound, you can do a lot. Okay, so I want to now, so this was kind of a table where we characterized everything together, where you had the iteration complexities, but it's almost unreadable in a short period of time. What you want to take from this is that you have geometric rates of convergence. You can claim almost show convergence in at least 2 of the regimes. We couldn't show it in the asynchronous game. And you can derive complexities, and you can tease out the level of impact of the number of players, as Matthias was inquiring about. So I want to kind of switch gears now and move to the distributed regime, right? So one of the avenues where game theoretic models have been of relevance, particularly in the context of networks, is that they provide you with a control so they enable a flexible control paradigm where agents autonomously control their resource usage to optimize their selfish objectives. And so you can actually design games whose equilibria maximize some other welfare function, right? So there's been a lot of work that Jason Martin and Jeff Sharma have done in this, and this has, of course, led to a stream of research. And so our focus in this case is to look at the aggregative regime. So in an aggregative game, and this comes from the work by Martin Jensen in 2010, essentially what happens is the coupling across players is not arbitrary. It is through the aggregate. And then there are variants of this, okay? There are variants of this. But notice here that essentially, rather than having an X minus I, it's X bar, where X bar, in this case, is the aggregate. And this is by no means, a very unlikely circumstance. When you're looking at flow control and communication networks, when you're looking at Cournot games, essentially you have connectivity across players through the aggregate. Okay, so this is not something that is altogether unlikely or rare by any means. Okay, similar kinds of assumptions, convexity and the existence of a stochastic oracle. And so there's a lot of work on distributed algorithms, right? And my colleague Angelia, whom we first started this work with, is done tremendous work in this area. So this comes from the thesis of John Cyclic in 1984, where they looked at consensus and distributed optimization. There's work, there's again a lot of work done since then. Amongst the earliest work, along with so we did some work in 2016, Angelia and I, with our student, where we looked at gradient response schemes with consensus for aggregative games, where we looked at deriving asymptotic guarantees. But since then, there's been a lot of work done as well. So there's work done by Sergio Chromatico. There's work being done by Lacra Powell. So in our key difference here, of course, is we're looking at aggregative games, and we're looking at the stochastic regime, which also has now seen a lot of interest. Okay, so we're looking at settings where we essentially have players who cannot observe rival strategies. They interact through a connected graph. Okay, and essentially you have some sort of adjacency matrix which we prescribe, and this matrix is is defined in this fashion, and we require that A is doubly stochastic. Okay. So our goal is to design a fully distributed algorithm. So essentially, there is no central coordinator in this particular regime. And this is distinct from some of the other efforts that others have made in this regime. Okay. And the question here is that under what conditions can we achieve the best known deterministic rates of convergence? So for instance, if I give you a strongly monotone problem, where if you look at the concatenated gradient maps, that map is strongly monotone, we know we can recover linear rates of convergence. Under what conditions can you do that here? And how should you tune the communication requirements to ensure that? Okay. So here's the algorithm. Okay. So this is the gradient response. I'm going to talk about both, but I'm going to focus on the best response. Now, in the gradient response scheme, essentially what you do is that each player maintains an aggregate by communicating with her local neighborhood, which is given by n script I. So n script I is a set of nodes that player I can communicate with. And essentially it takes the information from these neighbors and it averages across them, and it uses this estimate instead of the X bar that I talked about. It doesn't have the X bar. It doesn't have access to it. So it needs to learn this, right? So it uses this, and then it computes a projected gradient step. Now, unlike in the past, here we assume that I'm going to instead replace the expectation by a sample average with a batch size of SK. Okay, and so for those of you who've been looking at these mini batch type schemes, this is a mini batch type framework. Okay, and then you essentially take the step and then you update V sub I k plus 1. Okay, it's a very simple algorithm that is inspired by the distributed algorithmic framework that has become so common and so powerful in both optimization and control. Okay, and so I don't want to go into this, but essentially what happens is that tau sub k. So what I want to remind you here is, if you look at this, essentially what you do is that you essentially run tau k communication rounds. Okay, so what I'm trying to figure out is how large tau k should be, at what rate should it grow to ensure that a suitable rate statement is met. So tau k represents how many times I need to communicate, and sk represents the batch size. So it turns out that if I raise tau k at a linear rate and I increase sk at a geometric rate, then I can recover a linear rate of convergence. So I can get the deterministic rate of convergence. It's not surprising, right? Because the more you communicate, the more the algorithm the more the sequence looks like the one that comes from a centralized. The more that you raise the sample size, the more the sequence looks like it's coming from a deterministic problem, right? So what we're trying to do is we're trying to mute stochasticity, and we're trying to mute the network structure by going through both sampling and communication, okay? And you're able to kind of recover statements which align very well with the deterministic statements, but these might be unimplementable, right? The requirements that you have here may be unimplementable because they're too onerous, right? That the communication requirements are too onerous. I should point out that some of this work in terms of trying to see, what the communication requirements are was, at least to our knowledge, was first done by Mura and his students in CMU in 2014, where they also looked at this for the context of optimization. Okay, for the context of optimization. So this made us think, well, suppose I change this geometric rate to a polynomial rate. Okay, and this polynomial rate is, this exponent is given by nu, and I can tune nu. Okay, I can make nu, if I make nu large, it means that the communication rates and the sampling rate, so in this case, it's the sampling rate. So the sampling rate is growing at a much slower rate if nu is small, and if nu is large, it's growing at a faster rate. So a lot of this comes down to how costly it is to, in some sense, generate a sample, right? For those of you who work in simulation theory, you'll observe that in some settings, like if you're doing a queuing simulation, getting one sample might take you a day, right? But if you're looking at machine learning problems, it may be that, that getting a sample is very cheap. And so what we also wanted to do was to develop techniques and analysis which respect the cost of simulation. Okay, so if you have a costly simulation, then you want a small nu. And the question is, how does this affect your overall result? Okay, and it turns out that you can actually show that you can get these types of sublinear rates based on, so you get this polynomial rate of convergence, which inherits the same exponent that you use in the sampling rate. Okay, not surprising. Okay, so this is, I want to just pop over to the, so I want to pop over to the best response scheme. So the best response scheme is very similar. Instead of using the expectation, you use the sample average. Now you might ask, can we use the stochastic approximation framework I had before? Yeah, you can do that. You can try and do that, and that'll give you an exact solution. Okay, but we've used this, and it allows for the analysis is a little easier maybe. Okay, again, similar things. Okay, you essentially run the tau k communication rounds, increase the batch size sk, and what you're able to see is something very similar. You're able to see that you get geometric convergence, and if you change the sampling rate and make it polynomial, you can get polynomial convergence. Okay, so similar results. And what is crucial from this, and what you want to take away is not the fact that you can get these results, because it's not altogether surprising. What is useful is that you can actually start looking at polynomial growths and sample size, because they allow you to deal with the onerous impacts of growing the sample size, which might not be possible in certain regimes. Okay.
Is there a way to estimate the exponents here? Sorry.
Yeah, go on.
Is there a way to estimate the exponents here in the tau and in the S? So the U and the V, can you estimate
those are what you've chosen, Matthias. So what I do is that in this particular case,
okay.
So we choose that. So I prescribe that after I go through K communication rounds, I then choose the sample size to be K plus 1 raised to nu. And so this U and V, nu in this case, are user specified. So if I choose V to be large, then what happens is I get a benefit in terms of the convergence rate, but then I'm spending a lot of time sampling.
Okay.
Okay.
I see.
And so what you notice here is that you get similar behavior in terms of the oracle complexity, and you can see it because the statements are quite similar. Okay. And so this is just a way to kind of compactly represent this. I want to stop here. I mean, I think this is, okay, let me just kind of summarize the results. Essentially, we were able to produce a variance-reduced version of the proximal gradient and best response scheme. You get linear rates, and of course, you get polynomial rates if you use a polynomial growth in the batch size. This works for strongly monotone, and CPM here refers to the contractive nature of the proximal best response map. Okay. The distributed variance can also be analyzed. Here we have statements regarding the communication complexity as well. And you can see that if the iteration complexity is order log 1 upon epsilon, you get a log squared that shows up in the communication complexity. So I want to just spend 2 minutes here and talk about other stuff which to at least kind of introduce a conversation. So one natural kind of weakening of this is what happens when you move to merely monotone problems. Okay, when you want a distributed algorithm. It turns out there's some work that Sergio's been doing with such similar questions, but they've been looking at I believe, the setting where they have a central planner or a central coordinator in a fully distributed aggregative regime. So I should say that Sergio's work actually, in the sense, can allow for more general problems, but then they require this coordination to the best of my knowledge. In our regime, we don't require the coordination, but there's no free lunch, so we end up with a slightly more restrictive class of problems, i.e. the aggregative setting. And so we've got, that work should be coming on CDC, and I think we're in the midst of just sending out that paper. And so that's, and how do we deal with that? We deal with that using iterative regularization. But there are other ways. I think Sergio is using some of the work that Yura Malitsky's done in terms of using projected reflective gradient methods. What about non-convex regimes? So we've also looked at potential games where it's complicated by uncertainty, and you can get similar types of results there by combining stochastic approximation with some of these best response frameworks. But I think I'll stop here because I want to make sure that I leave enough time for questions. So I'll stop here. I'm sorry for running over a bit.
Okay. Thank you very much. It's a plethora of results indeed. A lot to take away, but thank you very much for this nice presentation. So we have some time for questions. Yeah. I would have a question already. So in the computations, in the distributed setup, none of the bounds somehow reflect, or maybe I missed that point. So is the graph A, the matrix you have there for the consensus step, is there some conditions you have there as well for the matrix A besides
so A requires, of course? A needs to be doubly stochastic. And so I had that, I think, all the way here. But it was so here.
Right. Okay.
Yeah, I need some requirements, but it's a good question because there's a lot of work going on in distributed algorithms where they've been pushing a lot of these assumptions, pushing them back. And given that this is the first work, the question for us is, of course, now that we've got this result, to what extent can we kind of push some of these assumptions back now that we have results? But yeah, we haven't probed that question. We've been looking more at the distributed question because for whatever reason that seems to be more relevant. But in the sense, and I think Matthias, you'd appreciate, or you'd probably have more questions in this regime because I think you work on games. So I believe there's been kind of emerging interest in Bayesian Nash equilibrium problems, a host of other problems where some questions like these might assume relevance. But I'm curious whether your background in games and economics suggests any new questions or any avenues that are worth considering.
Yeah, so I mean, what would be definitely interesting is to see what can be done outside the very nicely structured regimes you have looked at here. So convexity, of course, the convexity assumptions you have in here are sometimes not so easy to verify, right? The joint monotonicity you have on the operator is something that I don't know, doesn't appear so
No,
natural.
you're right. In fact,
application.
that's a very good question. So I think monotonicity requirements are often can be weakened if you're looking at gradient-based schemes. But I think one of the big challenges has been on the best response side that a lot of the convergence theory is tied to this spectral property. And one of the things we're trying to do is how do you deal with weakenings of that spectral requirement? And there are ways to do it, but in some sense, that's a really good question. Even the twice continuously differentiable requirement that we have is a strong requirement. It doesn't hold in general, right? But sadly, that was inherited from the best response structure that we started with. But yeah, that's clearly. What else? What else do you see as being kind of concerning in terms of applicability of this point?
I'm not maybe the best person to talk about applications here, but I mean, what from a computational perspective, what would be also interesting to see, I mean, you said something at the beginning, you were interested in settings where you have some non-convexities somewhere.
Yeah.
I was not sure whether you have non-convexities then in the objective or whether you have non-convexities somewhere in the feasible set of the agents, right?
Oh yeah,
so when you
that's
think about some combinatorial elements, for instance, in your feasible set.
That's a very good question. I think so let me be careful. We've looked at two settings which are of relevance. One is the setting where you have non-convexities you could have non-convexities in the player problems, but they abide by a potential. So player specific problems are convex.
Okay.
But there's some potential function. The overall problem may not be nice. And in that regime, best response schemes, as you know, for potential games, under some conditions, you can show convergence. But the other setting that we've been looking at is the setting of multi-leader, multi-follower games.
Okay.
So those are games, as you're familiar with, essentially you have Stackelberg leaders competing, and essentially it's subject to equilibria to the set of so essentially you have a set of followers, a set of leaders, and the follower equilibria are characterized by maybe a variational inequality or a complementarity problem. And in that regime, what can you say? So it turns out in that regime, it's a little harder because even existence is problematic. So we've been able to show some existence statements, and we're trying to see if there are subclasses for which we can show convergence, because that is a nastier problem. So that's where you have non-convexity in the sets. In particular, the sets don't even have, the feasible set doesn't even have an interior because you have complementarity constraints. But yeah, that problem is significantly harder.
Interesting. And I don't want to put it here as a dialogue, so maybe some other people also have questions.
So there was a raised hand by Sosa, but he's gone.
Okay. Oh, sorry. Did I miss it? I'm sorry. I can't.
No. Yeah.
Okay. So wait, Radu, do I have to do something? You said, or is that person?
No, everything's fine. I think, yeah. So let us ask for further questions. So then we should stop here, Matthias.
Okay, yeah.
So thank you so much.
Thank you.
And so this, again, I really enjoyed it. Thank you again for having me. And Matthias, I owe you a separate email. I'll be sending that.